So welcome back, everybody, and we'll continue building on our introduction from last week and go into a little bit more detail on some IDE stuff and GitHub today. Reminder, there's the book for the semester. The 10th edition is what I'm working from. And here's a list of stuff that I'm going to try to go over today. We'll see how far we get in that before I run out of energy to talk. You guys are lucky that my order of classes is kind of swapped around this year, so you guys get first crack at my voice. So in previous semesters, this would be my second or third class of the day, and sometimes my voice gets a little cracky by the end, but it's all nice and fresh, and I've got my hot tea, so I think we're good for a little while. So we'll see how far we get here. So one of the things, I'm not going to go through every single one of these terms, but one of the things I wanted to point out was, pirates talk like pirates, programmers talk like programmers. There is a terminology to learn if you're going to become a programmer. It varies slightly depending on what language we're referring to, down to the keywords and the operators and list of things like that when you get down into the nitty-gritty details. But at the higher level, a lot of these terms are just things that you're going to need to be familiar with and start using them in your common language. Some of this we probably already got out of CLP 1000, so it's review hopefully. But some of this is going to be new as we start talking about a higher level language like Java as opposed to Python. Hopefully we're going to be doing more debugging. Java has a compiler as opposed to Python. One of the things that they probably pointed out to you in CLP 1000 is that no matter what high level language we're talking about, whether it's compiled or interpreted, the CPU on your computer system really only knows machine language. The basic low-level instructions that it was hardwired to support from the manufacturer is what it knows. And so no matter what language we're talking about, they are all tricks and syntactical devices to do stuff that we commonly want to do in machine language. I have tried actually to see if any of the common AIs available do a good job of creating code directly in machine language, and they don't. Anybody got a guess as to why that it might be, from what you know about AI and how they're developed?
Because they were just trained on data, which is English.
Yeah. Yeah, an interesting note, one of the things earlier in my career that I was exposed to was our company was working with some software. They had bought a company in, I don't remember which South American country it was, but some of the source code that they got from purchasing this company, I mean, it's all in the same computer language, right? The computer understands that, so there's no English Python versus French Python, etc. It's all just Python, right? Same with Java. But the comments were in a different language, and so we're all getting our little English to Portuguese or English to Spanish or whatever country it was dictionary to try to figure out what the comments meant so that we could understand what the programmers were saying. So yeah, but let's say all of the instruction or all of the training for an AI in Java were done with English-speaking programmers. Well, then if you're a Spanish-speaking programmer and you ask the AI to generate code for you, it's going to know because it's got lots and lots of examples of how comments look in English, but almost none in other languages. Now, also, it's probably trained on how to convert English to Spanish or Spanish to English or etc. So it might be able to, as a secondary step, take those comments and convert them. But the whole point is that it has to be trained on data that allows it to develop those pathways in its neural network to support doing that. So if you go to GitHub, there's not a lot of code out in GitHub and the vast number of public repositories that you can search through that have machine language posted to GitHub and people out there editing the hex digits of the code to manipulate it to do what they want it to do and then submit revisions. It just doesn't happen. So the AI doesn't have a lot of training data to use. So you get the same kind of results right now trying to develop machine language solutions to your questions out of the box that we got several versions of the AI ago when it was not very good at anything, frankly. And you ask it to do some simple programming task in Python and it generates crappy, buggy code, right? Because they hadn't been trained very well or extensively or using the refined training algorithms of today. So anyway, that's just an aside, but the tools that we have, the compiler that we have, takes our Java code and converts it into machine language so that it can be executed. And there's actually a caveat to that, like we mentioned last time. Languages like Java and C# aren't even going directly to machine language because, as we talked about last time, that's actually not great in some scenarios. Back when we had a very diverse set of hardware, RISC versus CISC, complex instruction sets like the Intel platform, or reduced instruction set computers like some of the older ones. I don't even know if there's very many of those around anymore. I can't even name one off the top of my head. But you would actually need to develop vastly different machine language code to execute the same higher level language instructions back then when we had a much more diverse set of hardware. Now, most of the computers that you're going to have access to are going to be based off the x86 instruction set, and so there's maybe not that need for it. But at the time, it was a big benefit that you could develop code in Java and have it compiled into this intermediate code. And do you remember what we call that in Java? It's called something different in C#. Do you remember what we talked about last time that we call that intermediate code?
Bytecode?
Bytecode, yes. That's what the Java people that invented Java called it, is they compiled Java into bytecode, which is sort of like their own set of low-level instructions, but it's pretty easy to develop another process that converts the bytecode into whatever machine code instruction set that they wanted to at the time, because they developed it to support doing that. So it was a big advantage back then. I don't know that we flex that advantage nowadays as much as we did back then, but it is what it is. Java still works the same way. C# works the same way, and they call it intermediate language. So, what else we got there that might be new for, okay, so depending on who you had for COP 1000, you may or may not have gotten into much object-oriented discussions. Lots of times we're happy if people can write programs at all coming out of COP 1000, but if you read ahead in the book, one of the next chapters that you get into after that semester ends is talking about how to do object-oriented programming in Python. So you may or may not have already got there. But some of the terms that we use around object-oriented programming, they're in one of the chapters that we'll get to down the road, but encapsulation. So when we imagine some kind of an object, we encapsulate it in a Java class. So we're gonna talk more about what those terms mean, but I just want to throw a bunch of it on the wall so that kind of glance through this list and see, make sure that you know what these terms mean and become familiar with them ahead of when we start actually using them to do what we're doing. Okay, so we also kind of threw this out there last time, briefly. So hopefully this is the second time maybe you've seen it instead of just the first time. So simple program that I typed in last time. I think I used Notepad maybe to do it last time. But we start out with I've got comments through here. I'm trying to set an example for good programming style by using comments to indicate what I'm about to do, so that, hey, if I forget what that keyword means later, I can come back and remind myself what it was I was intending to do here. But we have a public class called hello. Inside that public class, we've implemented a method called main. That method is a static method, and it's publicly accessible to anybody that can see the object in this compilation environment, in this scope, we would call it. It takes an array of strings as arguments. Okay, and you can imagine if I'm typing this or executing this on the command line, if I say my program space A space B space C, the A, B, and C are the list of arguments that are going to get passed in here. And by convention, usually the first one, args subscript 0, is the name of the program in case you might want that. So it basically just splits that string into all the different parameters that were entered on the command line and provides them to the program as input as an array of strings. Nice and convenient so you can get access to them. Because that's one thing we commonly want to do, is get access to what parameters the user entered. And then this program does one simple thing. It prints a line to the console that says hello world. So as we talked about last time, the process of creating a program means typing in something like this in text format. Depending on what editor you use, you may or may not get the nice color. We call that syntax coloring. Puts each different kind of component. I don't know exactly what the list of all the different colors and what they get assigned to are, but it makes it easy to kind of spot different things as you glance at your program than if it's all just black on white background. So, but Notepad doesn't have that. So anyway, we'll save that text file in a file called something.java. So the .java tells the operating system this is a Java type file and associates it to whatever program. And that gives us the ability to, if we see this in File Manager, we can double click on it and it knows which standard editing tool we want to use to open that file. I want to point out this line down here. I think I might have mentioned this last time, but in case I didn't, I'll say it again. I try to repeat this early and often because it's very helpful. It can be very confusing if you're using a computer with the default file manager settings, because it wants to hide the file extensions on all the files that you're looking at in a folder. Some of them it knows, oh, you probably want to see the file extension on this, but I'm sorry, as a programmer, I want to see the file extensions on everything. It's not going to cause me to freak out just because every file in this folder has an extension on the end of it. I want to know what type of files those are. And my brain does not associate the little tiny 16 by 16 pixel icon that they put next to the file as to what type of file that is. Sorry, I've long ago stopped trying to memorize icons to file types because they change all the time. So go into your settings in File Manager and change the settings so that you view file extensions all the time, and it'll help a lot. If you haven't done that on your development machine at home, I recommend you doing it there too. You can always change it back if you don't like it, but it really helps when you're trying to find that file to turn in Canvas, when you're browsing for the files on your local computer, to be able to turn in the one that's hello.java instead of the one that's hello.config or hello.data. So you'll thank me later if you just trust me right now and go do that. Unfortunately, you know, these computers in here, they reset every time we reboot them, so you probably have to do it every time you come to class. Gets a little annoying. Maybe they'll fix it one of these days, but we'll see. Okay, so we've got our hello.java. The next thing we want to do is Java C. So we're going to compile that Java file. What that does is it takes the .java file as input and it outputs a .class file. And guess what that .class file has in it? Bytecode. So that is the portable version of the Java distilled down to bytecode by the compiler. And so at some point in the future it will get executed. It's kind of a gray area. You know, we would call something like Python an interpreted language because when you run the program, the Python executable is reading instructions one line at a time and converting them to machine language and executing them right there, just in time. But in Java, you know, as opposed to C++, where when you compile a C++ program, you get machine language code in an exe right then. Okay, there's no further translation needed. It's compiled for that processor right then and there, and it's ready to be run straight from machine language Go. So that's a little bit more efficient, right? Because Python happened to reinterpret the same line that it just executed a few seconds ago again. That could be a little inefficient, but C++ has already done it all straight to bytecode. It just executes it natively. Is a lot faster. Even if, you know, one of the algorithms is more or less efficient than the other, C++ is generally going to be faster than the Python code just because of the way they're architected. Java and C# are kind of in the middle because they're pretty darn efficient because the bytecode and the intermediate language is pretty much a one-to-one execution of, it just converts it to machine language and executes it. There's not a lot of processing that needs to be done at execution time, but there is some. So you'll notice a little bit of a degradation, but most people that use Java and C# are okay with that. That's fine to, you know, for the benefits that they get otherwise, they're happy to sacrifice a few clock cycles to do that. So when you say Java and hello, hello is the name of the class. So you notice up here, public class hello. That's what it's looking for when you execute it. And so it'll open that up and start converting. It'll look for the class named hello, look for the main function inside there, and execute that function. So then we'll see the words on the screen. Good, good. Then it'll exit when it's finished, and we're done. So that's a simple console application or command line program. I'll use those two monikers synonymously. But they, you know, relatively mean the same thing. Any questions about that process? Like I said, I went through it briefly last time. Hopefully this is mostly repetition, but I'm trying to throw more words around it to give more context. Make perfect sense to everybody? Okay, now I'll contrast this, expand on this a little bit. If we're talking about a game, or if we're talking about a Windows application, something that's got some kind of a GUI implementation, graphical user interface, this would all be relatively the same. The difference would be in a game, you typically have what we call a game loop. So the game's going to continue running. You don't have to execute the program every time you want to make a move in the game, because it gets a little tedious, right? You run the game once and the game continues playing while you're pressing keys or providing input. Anybody ever play one of those old text-based role-playing games like Zork? There was a whole generation of them that came out early in my useful lifetime. But you know, you basically would just sit there and have a conversation with the computer back and forth, as you play the game. Well, so the difference between that, the structure of a program like that and this is that instead of just printing a line of text to the screen and exiting the main function and being finished, because when this main function ends, it executes the last instruction in this function, it returns, the Java program exits, and it's done. Well, with a game, we would have a loop that would never end inside this main function. And then it would call and use other objects, call other functions, and do other things in the middle. But when it was done processing a turn, then it would loop back up to the top and do another turn. Ask for more user input, wait for more keys to be pressed, and it would just never exit until, let's say there's some button that you drew on the screen that says quit. You push that, and then the program says, oh, if they hit the quit button, then exit the loop and exit the program, and then the Java program ends. So that's the difference. It's the same structure to start with. It's just that once you get into that main function, you do all kinds of complicated stuff. And a Windows program is very similar to that, but you have a window loop. So you have a main application, and inside that application, it starts up a window, and then whatever the program tells it to draw in that window, menus or toolbars or status bars or other stuff in there, all that stuff gets drawn, and then it waits for mouse clicks and keystrokes and stuff, and it just keeps looping, waiting for those things to happen, very similar to the game loop. So really a Windows program is no more complicated than that. It's just a program that loops, continually waiting for input. Okay, moving on. So at minimum, I like to talk about minimum. If you're in a pinch, some internet cafe, if you can still have those, I'm showing how old I am. At minimum, you just need a text editor like Notepad. You need the Java compiler installed. You need the Java virtual machine, which is the environment where the program will run, and and an idea of what it is you're trying to accomplish. And you can create Java programs. That's all you need. You don't have to buy anything. Java is available for free, so you can get started out of the box without any big outlay or without a whole bunch of stuff to do. I mean, you do have to download the compiler and the Java virtual machine, but And then next question is, on these machines that the college has so graciously already provided and set up for us, what did they give us? So if you look on your program to see what they've installed, we can scroll down through here and see a number of programs. We've got the Eclipse IDE for Java developers. So Eclipse is one very popular environment. JetBrains is where the IntelliJ IDE comes from. They have a whole bunch of other tools for Python, for web development, etc. This is the actual Java tools. The compiler and the runtime environment added these shortcuts to your menu. I'm not sure if there's anything else. I mean, obviously there are other Java IDEs out there. Visual Studio Code, you can do Java from Visual Studio Code also. You might have to add some plugins or add-ins, whatever they call them, to get that configured and working right, but I'm sure there are YouTube videos on how to do that pretty straightforward, because a lot of people do it. So, from my point of view, that's probably your main three, unless you really want to use Notepad to develop your Java programs in here. You're probably going to want to use Eclipse or IntelliJ or Visual Studio Code. Anybody using any other tools than that yourself, or played around with them, or read about them? Okay, but they're pretty good. I really like IntelliJ simply because I used Visual Studio starting out and got used to the user interface paradigm that it used. And so IntelliJ was a very easy transition for me, because things kind of were in the same places and called the same things. as opposed to Eclipse, which was a bunch of Java developers that were anti-Windows and Microsoft that said, no, we don't want to do anything similar to them. If Microsoft did it that way, it must be bad. So they developed their own way of doing stuff. Okay, I'm being a little biased there, but there's nothing wrong at all with Eclipse. Like I said, it's just for me, it was like oil and water a little bit, and I felt more comfortable using IntelliJ. But you're welcome to use what you want, and I'm just joking when I say bad things about Eclipse. So yeah, we've already got those tools on here. And as I mentioned before, I think last time, before the end of class, when you run these for the first time, you may be presented with a challenge to enter your license information. And because it's a really good benefit, not because I'm biased towards one or the other, I would recommend that you go to JetBrains and take advantage of the fact that they offer a free 1-year license to students. So here we are, beginning of September this year. If you go get a free student license now, it'll go through, first week of September next year. And then you'll have to go out and say, yeah, I'm still a student. Can you renew my license? And they'll give you a new thing. And what they do is they give you a code, some gobbledygook looking text, and you enter it into the screen when you run the IDE. Now, I complained last week when I tried to run this and it was not using the site license that we have for student for educational. And so maybe you don't have to do that coincidentally here. Let's try it. Hello world, not change anything, create. See, I think they must have worked that out. Because since they restart and reset the machine to their beginning settings, it was a little annoying to have to go enter that license information every time when we were supposed to be good as a school to be able to do that. So yeah, it looks like they fixed it, which is great. So we'll notice a few things about this. There's a whole bunch of other folders and files and stuff. And it looks a little bit different, but you can see it's still got the public class main. It's still got the public static void main. Still got the arguments passed in. They threw in a little print, and then they were fancy and did a little loop and said, oh, let's print the numbers from 1 to 5. Okay, fine. It's got some syntax coloring going on, some other little arrows and stuff over here. Breakpoint has been set already. So this is what IntelliJ gives you, I guess, to start with. Great. I didn't have to reinvent the wheel. One key thing that I'll point out is, even though I told it to call the project Hello World, the class name that it used for this file is main instead of hello or hello world that I used in my example. So what does that impact? Well, typically it's going to complain if the class in the file is not the same as the name of the file .java, right? So main.java and public class main, that pretty much has to hold true for every file that you create in a Java project. Okay, we're probably going to eventually have programs that have multiple files and multiple classes, and we're calling them, instantiating them, deleting them, all kinds of stuff to do what we need to do. But each of those files is going to start out with, main.java, public class main, or myclass.java, public class, myclass, right? File name and the class name in the file need to go together, because Java makes some assumptions there, and we have to kind of go along and support that. And if I forget, by the way, to zoom in on any of these things, remind me. I'll have to figure out how to zoom in on this in this IDE. For Notepad and Visual Studio, it's just holding the control key down and using the wheel on the mouse, but that's not working on IntelliJ, and I've forgotten what the actual way to do
Try
it is.
control plus and minus.
What is it?
Try control plus and minus.
Control,
And then hit the plus.
no. Anyway, there is a way to do it. I just have forgotten what it is. Okay, so I'm not going to save this. We'll come back to stuff like that. Yeah, so here's what I'll say, editorial. Gaining experience with one or more of these commercial IDEs is of a benefit to you. That's one of the reasons why we lobbied to get these IDEs installed on the computers here. Because having familiarity with the tool, and then you go in for an interview for a job, and you say, oh yeah, we used IntelliJ, or we used Eclipse at my school, so yeah, I'm already familiar with that, I'm good. That will help you, that'll be a plus. However, like I said last time, be careful enabling too many AI and autocomplete functions, because you don't want your code that you submit looking like AI code and get you in trouble there. So if you see any of that kind of stuff happening, the little hairs on the back of your neck should stand up a little bit. And just for class purposes, don't use it. It doesn't do you any good to have the computer do all the code. Risk getting a bad grade because something detects AI usage, and to not learn what it was that you were supposed to be typing in. There's this thing with memory where I was always a very auditory learner. I would always try to sit in the first row or two in class, because if I could sit there with my arms folded and just listen to what the teacher said, I would retain quite a bit of it. Other people are like, I didn't understand anything the guy said, but I went home and I read the textbook. Oh, and that made perfect sense. That gave me exactly what I needed to know. They're reading learners. Other people taking notes. Something about the hand-eye coordination of writing it down on a piece of paper sticks it in your memory, right? Different people prioritize different things with developing new pathways in their brain, and so different people learn different ways, is what we would say. I want you to get the information best the way you learn best, so that you get it the best, okay? I know that typing is one of those things. If you type the text in instead of letting it autocomplete, your brain will remember the keywords better over time. I'm not talking about 6 months or 2 years or 10 years from now. As soon as you get out of here and somebody's writing you a paycheck to do this stuff, they're going to expect you to use AI to do the work and not do all that typing. Typing is inefficient, okay? But, and it's weird for me to say that. One of the things, as recently as last semester and the semester before, that I would tell students is, if you haven't already taken a keyboarding class, that was the thing in my career that I can remember taking my productivity from here and going way up to here, is when I could type things on my keyboard that I wanted to program without looking at my fingers. Okay, and I knew people my whole career that typed programs with 2 fingers, their 2 index fingers, okay? Now you guys are all fluent on your phones or your tablets, and you probably do all your typing with your thumbs, right? So I get that. I get it's different in different environments, different generations, and different purposes that we're trying to accomplish out here. But if you have a chance to take a keyboarding class where they make you get up to 50 words a minute or so without looking at your fingers, that will vastly improve your productivity. Except that now your bosses probably don't want you to type anything, because they want you to tell the UI what to do, and they'll give you the algorithm when you're out there getting paid to do it. But we're not here to get paid to write as much code as possible in an hour. We're paid to learn how to imagine these algorithms and convert them into Java code. So don't do it. Learn to type for this class. Yeah, so just for now, put that off. Just put it off for a while. Okay, I'm going to talk a little bit now about GitHub, which is really, really cool. I think I mentioned this also last time at a high level, that we want to start thinking about a portfolio and developing a portfolio of things that we have developed personally and that we can talk about to a potential employer. And you'll take those things and you'll think, ooh, well, what if I took that and I did this or added that to make it something more attractive to stand out in an interview or stand out, you know, when you're submitting your resume somewhere and they go look at your GitHub presence. So we want to do that. Now, that's a big topic. I'm going to try to stick to the pragmatic approach here and just give you enough as we go so that you can get it to work, because this is not GitHub 101. But I'll give you the high level intro to this. Okay, Git is one of a long series of competing source control systems, both internal and external. Microsoft used one internally that it never was even shipped as a product. It was just what all the programming teams used inside Microsoft. I think it was something creative like Source Code Manager, SCM. But then they did put out one called SourceSafe. A lot of people used it for quite a while. It had a nice GUI interface, so it wasn't all command line. It was a little bit more approachable to people that preferred, you know, graphical user interfaces as opposed to the command line. But then Git came along, and Git pretty much pushed everything else out of the way. And you know, you might still go to a company and they've got a different corporate-wide source control system, but most everybody that I'm familiar with nowadays uses Git. So Git is a set of tools that you download and that you run at the command line. Just like Java, just like Python, the programs that you download and you're going to run the commands, you're going to run Git and the commands, okay? GitHub is simply a public website and repository that a lot of people use to take their Git repository and push it remotely so that they can access it from other computers later. Like our model here is pretty simple, pretty practical. You'll create code here on your computer, you'll put it in a Git repository, then you'll push that to GitHub so that when you get home, you can pull it down from GitHub and continue working where you left off. When you're done at working at home, you'll push those changes back to GitHub. You'll come back here, you'll pull it from GitHub to your local Git repository, and you'll continue working. Or you can go to the GitHub website directly and say, it's time for me to turn that in, so let me download that Java file to my downloads folder and go to Canvas and upload the file to turn it in. Right? That's sort of the workflow that we're going for here. So there's a difference between Git, these set of tools that you install and you run from the command line locally, and GitHub, which is just a website and a public repository that you can push things and pull things from. Okay? Does that make sense? Git versus GitHub. To install it, I threw the command up here for you to be able to reference later if you need it. Winget is just, you know, one of the tools locally on Windows that you can use to pull something and install it. So if you do this command, you will be downloading this set of Git tools. Now, I'm guessing they're already installed on these computers, so we don't have to do that. Let's test that. Yeah, see in here, I can just use the control and the little scroll wheel. It's so nice. So if I just type Git, not recognized. Okay, let me see where. Okay, so it is installed in a couple of different places. In Visual Studio. That's interesting. So I could either take this folder and add it to my path. I'm going to have to talk to IT about this because I would really be more comfortable if we didn't have to do that every time we come to class. It'd be nice if it was already installed when we got here. Okay, or I can type winget install. Let's see if this still works. Yes. Okay, now when I type git and hit enter, it's there. And it gives me a little help message of a bunch of the common things that I can do, the different parameters I can pass, git clone, git add, git remove, git move, git commit, git push, git pull. Those are some of the common commands that I will use to use git. Pretty nifty. Okay, so we learned that no, it isn't just installed in a public or in the path already for us. So if we want to use it here, we'll have to install the tools like this shows, and hopefully at the end you'll see successfully installed. Or in any event, if you're at home and you want to use git at home, you'll need to do this command on your computer there. And that's not the only option either, because it is command line, and like I said, in the source safe days, people preferred a graphical user interface to the command line. There are tools. One of my favorite is Tortoise Git, which is a downloadable and installable file manager extension. So if you're looking at a folder in File Manager and you right-click on a folder, there's commands in there to pull the latest copy of the repository, push the changes, things like that. It makes it nicer to use with your mouse instead of at the command line, if you prefer that kind of thing. So if you like doing that, you might want to try at home Tortoise Git and install it. Sometimes, and I'll let you know, I don't memorize every git command. I'm not fluent, and I don't think I can honestly say that I've used every command and every aspect of Git's functionality. I'm a lot more pragmatic than that. I do git clone, which says, hey, there's this GitHub repository. I want to pull it down and put it in a folder on my local computer. You clone when you're doing that. I want to make a bunch of changes. I git commit those changes, which is like taking a checkpoint of those changes so you got something to restore back to. Yeah.
For people who don't like command line, they can use GitHub desktop.
Yeah, there's a whole bunch of them out there. Yes, I agree with you. Good point. Tortoise Git is not the only one, or even necessarily the best one. It's just the one that was the best one at the time I started looking for one, and then once I got used to it, I didn't want to change to something else. So yes, if you look for graphical user interfaces for Git on Google, I'm sure you'll find a whole bunch of them. And those are a couple of good ones that he mentioned. But, your mileage will vary. Mentioned this a little bit, we're going to start figuring out the object-oriented stuff. You need to know just enough to get your programs to work for now. Like I said, that public class main at the top of your program, what the heck is that? Why do I have it? Why does my program stop working when I have a typo in it? That kind of stuff. You just need to know that it's required for now, and we'll get into the object-oriented stuff at the appropriate time later. I mentioned, we have, when we envision an object like an animal object, we will encapsulate that as a public class animal, and we'll design the properties and methods of an animal inside that class. That's just how we do it. That's the terminology we use. This represents your class. You'll have a whole bunch of functionality inside the functions of a class, but the the set of public properties and methods of a class basically represents its contract. It's how you and the object will work with one another. Okay? That's a good way to visualize that for now. You saw the public static void main function in the example. Static things, when you say static, so non-static things by comparison are things that you can create multiple instances of them. You know, if I have this animal class that I just mentioned, I could create as many instances of an animal object as I want to, and the properties of each one can be set to different values, so that when you call the methods of those classes, those objects, the behavior will be different based on the data of each object, okay? But a static thing, a static object, a static method, that means there's just one of them. So if you create a static integer, we used to do this a lot in websites. You'd create a website program. You know, a website is simply nothing more than a program that receives HTTP requests and returns HTML text, right? You can write a command line program that is a web server by just your arguments are just an HTTP URL, and the output that it prints back is HTML. Then you've built a web server. Congratulations. But let's say that you wanted to display on your web page a list of the number of times that that page has been accessed, which back in the day before search bots and that kind of stuff was kind of a nifty little thing. Oh, look how, you know, it's kind of like the McDonald's 40 billion served sign, right? It was just sort of a nifty little counter to show, oh, look how popular my web page is. But if you wanted to do that, every single request that comes into the web server creates a new instance of the object, sets the counter from 0 to 1, returns the HTML, and then exits. So the next one that comes in creates an object, sets it from 0 to 1, and exits. So it never remembers what the previous URL was set to. But if you make that integer a static, now there's only one of them. So now each time a web request comes in, it increments it from what it already is to the next number, and you get that counter effect. So that was one of the first nifty things to use a static property in a program for back in the day. But it's the same thing now. Sometimes we want every single animal object to reference the same value. We can either make it constant or we can make it a static. So that's what static is. We'll learn more about that later. Yeah, and you know, Java, I think, existed before object-oriented programming, and they just kind of shoehorned the object-oriented stuff around it. That's the reason why, I mean, it seems a little bit awkward. Why do we have this public class main with a public static void main? Why couldn't we just get rid of the public class main out of the outside of it and just have the function? They're doing that to sort of speak to the fact that they want it to be seen as an object-oriented programming environment. So, yeah. Yeah, so there's our good old example. Not as many comments, but that's the, you know, basically the bare minimum. It doesn't even have the print statement in it. Anyway, you get the point. Okay, so the next thing we're going to talk about, let me see if I can fix my slide here, because that was supposed to be, let's see if that runs. Yeah, there we go. Okay, so here's the life cycle. You'll hear me use this here initially in the first couple of classes a lot. When you're working as a professional developer, you talk about this life cycle a lot, but it starts out, program manager will come and they'll talk about the project life cycle. And they'll say, well, a project starts off with inception meetings where we're talking to our business owners and they're telling us what they're going to give us $1 million and we're going to spend 6 months developing the software and then we're going to deliver it to them and we'll talk about the success metrics, blah, 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 blah. Inside there, we're going to have design meetings where we say, well, if they're paying us this much money and that's our budget, what software do we need to create? How many programmers and testers are we going to need to do that? And we come up with a project plan, a bunch of Gantt charts, and then we start week by week going through there and providing status reports, et cetera, et cetera, et cetera. And finally, at the end, we have a big party because we shipped it and it worked. Customer was happy, they wrote the check cleared, and now we're all happy and waiting for what the next project's going to be. That's what would be a project life cycle. And inside there, we get smaller and smaller life cycles. Like you have your workday life cycle, right? You get out of bed, you brush your teeth, you get some coffee, drive to work, et cetera, et cetera, et cetera, go to lunch. That's your daily work life cycle, if you will. So what I'm talking about here is the assignment life cycle. So if I give you an assignment, a programming task, and then you're going to follow a number of boilerplate intro steps in order to get started, then you'll do your work. At the end, once you think you're done, you'll follow some more steps for every project in order to finalize that, save it, upload it, and turn it in. Okay? So that's what I'm calling the assignment life cycle, the steps that you need to do pretty much and repeat with every one. And you want to just kind of learn these and become practiced at them so that you don't have to consciously think about them as much. You're just repeating them for muscle memory after a while. And if you get comfortable with what I'm calling the assignment life cycle here, that's going to mirror pretty closely when you're creating your own programs. You'll start following the same set of steps every time that you say, oh, I want to create something. You're not just going to run Notepad and start writing a bunch of Java code. No, that's not the beginning of the life cycle. No matter what you're going to produce, you're going to step back and follow some introductory steps before you even think of what the name of your program is going to be. So what we would typically do is we would go to GitHub first, and we'd say, hey, GitHub, I want to create, you log in, I want to create a new repository. And you'll give it a name, something that represents what you're about to develop, and it'll say, okay, it'll ask you some questions. I guess I should mention this so that it makes sense when you see them. It's going to ask you things like, okay, a lot of people create repositories because they're going to create a piece of software. Do you want to use the MIT license or open license, or there's all these license options, and all it does is it sticks a file in there in your initial project that says, here's the license text. It says, don't go copy my program, or you owe me money, or blah, 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 blah. It'll ask you some questions about that, but once you get through those, and then boom, you've got a repository. Now it's empty. It doesn't have anything in it except for, like I said, those little files that it may create depending on how you answer those initial questions. But essentially, you've created an empty folder that you can put stuff in on GitHub. That's all you've done at that point. You create a GitHub repository for the assignment. Okay, next, you're going to go to your local machine where you've installed those Git tools, and you're going to open up a command prompt, and you're going to clone that repository. So you're going to say git clone, and you're going to give it the URL of that repository you just created. And you're going to tell it which folder locally you want to create it in, too. Otherwise, it's going to create it in whatever folder. Like when I type command prompt here, it starts in the C:users FSW labs folder. Well, you may not want your assignment to go in that folder. So So maybe you want to create a subfolder or a folder called COP 2800 or something like that. Or you want to say on the command line which folder you want to put it in. But you're just going to say git clone, the name of the, probably HTTPS, the name of the repository, whatever the URL is that you get from GitHub, and there's probably an option here. I do better with examples. Show me an example. Okay, and then the name of the folder. So git clone / blah, 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 whatever the repository was called, and then something like that, the name of the folder that you wanted to put it in. So when you enter that, it's going to go out to GitHub, it's going to grab whatever's in that folder, which again, initially is nothing, or maybe the license file, maybe a README, whatever you told it to create. And it's going to take those files, it's going to create a folder, and it's going to download those files into that folder. In addition, it's probably going to put like a hidden .git folder and some other stuff. Like when you told it all that useful information, and eventually you're probably going to say, hey, remember that GitHub repository? Can you upload these changes back to it? So it needs to remember that URL of the repository. So that's what it puts in that hidden little .git folder. So it's just saving some little bits of details that it needs to know to remember what it was doing. But you don't care as long as it works. So git clone creates you basically a local folder where you can start doing stuff. Now, you can start creating their project. So you'll either run Notepad and create some Java files, or you'll run Eclipse or IntelliJ and you'll create a project, and that'll create a bunch of files and folders and all kinds of stuff. You'll run, build, test, iterate until, okay, it's about the end of the day, I want to go do something else now. You'll save all your files. Then you come back to command line and you say git commit. And when you say git commit, it's going to say, well, let me go compare the files that were in the GitHub repository to the files that are in this folder here. And I'll compare and see which ones have changed. And, well, actually, no, I'm getting ahead of myself. What it does is it looks in there and says, have any of these files locally changed from where they started? That's another little detail that it keeps in the .git folder, is what version you were sitting at with each of those files through some magic we don't need to get into. But when you say git commit, you're saying, okay, I think I got this okay, but I'm going to go make a bunch of other changes, and I don't want to lose this point right here in the code. So in case I get a bunch of changes and I'm like, no, I don't know what I was thinking, I want to get rid of all that and go back to what I had, you can revert to this commit point. So you can make a bunch of changes, commit them, make a bunch more changes, commit them, make a bunch more changes, commit them, as many times as you want here locally on your machine. Then when you're ready and you think you want to save them because you're getting ready to go home, or you're at home and you're getting ready to come to school, you push them. So you say git push, and it'll take all the files and push that version of those files out to the remote GitHub repository and just uploads the current copy of them. And then, now they're saved. You'll go to Canvas and you'll upload that file and turn it in. So that's your assignment lifecycle, in a lot more words than I probably required to explain it. So you git clone to create it. You go to GitHub and you create it. you get clone to pull a copy of the created repository locally, you make your changes, you git commit them, then you git push them back to GitHub, and then wash, rinse, and repeat. Okay, makes sense? And it makes a lot more sense after you've done it a few times. So I do have this diagram. So you've got other people out here too. That's another one of the beautiful things about GitHub, is it's useful, if that's all you ever use it for, is just creating a portfolio of the code that you've created. It's immensely useful for your own posterity's sake. But other people with access to that repository can also be making changes and committing stuff and pushing it to that repository at the same time. So it works great in a team environment. You know, when Microsoft bought GitHub and started using it, they instantly became the largest consumer of GitHub because they put the Windows source code into GitHub. So then all of the employees at Microsoft started managing code changes to Windows in GitHub, and it's millions of lines of code. Just that one thing. Not to mention the millions of other people out there that are also using GitHub. So it's been heavily stress tested and functionality tested, and has gone through a number of improvements and revisions. I mean, even just building. So Microsoft used to use the country of Puerto Rico to build Windows until a hurricane hit Puerto Rico a number of years ago and took down the data center. Well, Windows still needed to be released every month, so they had to scramble and distribute the build system to other places around the world so that wouldn't happen to them again. But yeah, it used to take the whole country of Puerto Rico and a data center there to build the next version of Windows once all the changes had been checked in. So it's a pretty big program, and if GitHub can handle it, it can handle our small repositories, I guess is my point. Okay, so changes pushed from other users, or you create this new repository, but it starts out in this initial state. You've got a remote repository in GitHub. So step one is you clone it. Now you've got a copy locally that you can work on. Two is you make a bunch of changes to it. You commit to your local repository. And I didn't put on here the step of, I guess step 4.1 is, if you don't like those changes, you can revert back to a previous place where you committed. You know, you can roll that forward and backward if you need to. But step 4 is assuming you're happy and you want to move forward. This is a little different than the simple use case that I mentioned. Before you push your changes remotely, if you're working in a team environment, the first thing that you need to do is pull the changes, and you're like, well, wait a minute, I just made a bunch of changes locally. If I pull what's on GitHub down to my local folder, won't that squash and overwrite all of the changes that I just made here locally? And yes, it would, but Git knows that that can happen. So when it pulls down the remote copy locally, it merges the two. And if you and one of your coworkers was working on the same area of the code, you might get a warning that says, hey, there's a merge conflict here. You and Jim were working on the same piece of code. So what it does is it puts little markers in the file, and you have to open that file and figure out which one of the lines of code, Jim's or yours, that you want to keep. So you work that out and resolve the merge conflict. And once you're done, great, now you're happy. Now you push your version that's been merged with their changes back to the remote repository. And then you're back to the starting point. Now your local copy matches what's on the remote, and you go back to step 1. Well, you don't clone, but you know, you might pull. So anyway, like I said, life cycle. Good stuff. Okay, next thing I wanted to mention was flowcharts and pseudocode. You know, we made such a big deal of flowcharts and pseudocode in COP 1000, right? So we're going to do flowcharts and pseudocode for all of our programs in Java, right? not so much. If it's okay with you, can we just say we've checked that box and move on?
Yes.
You know, the reason why we spend time on flowcharts and pseudocode is before we get into developing biases in your mind towards one programming language or another, we want to generically just start your brain to learn to think in an algorithmic way, right? So you start thinking of breaking down problems into solutions the way a computer would execute those solutions. Okay, so flowcharts are a visual way, pseudocode is a textual way of expressing the algorithm without the bias of a particular programming language, is the way I would say it. I mean, they don't, it's not like we're gonna say that they don't exist or it was a bad idea to learn them or anything. They're a very handy design tool should you find yourself in a situation where you need to think about the design and doodle on a piece of paper before you go to the computer, okay? So no, it wasn't all just busy work, but it has a time and a place. So I would say another use for them is if you want to communicate your idea to somebody else. You know, you don't sit down and paint a picture of your cousin if you want to describe to your friend what your cousin looks like, right? No. You can use with a few words at a high level and keep it vague and abstract and get your point across to somebody. And again, flowcharts and pseudocode are a good tool for just communicating between us humans what we were thinking of to communicate the algorithm. So they have their place. And there's other stuff too. I use quite a bit of, I use sequence diagrams quite a bit in representing the solution to something very complex and trying to represent how we're solving this problem to others without resorting to programming logic, which can get hard to read. Many program managers in software development teams have been programmers themselves at one time, but then they realize that they have, they lean towards the business side of things more than they enjoy writing code 8 hours a day. But they understand it. If you try to explain them a programming concept to get your idea across, they understand it because they were programmers themselves at one point. That's not what they want to do for 8 hours a day. So explaining to program managers and your boss and other people in using a sequence diagram or a state transition diagram and things like that, they're useful tools for communicating, but that's what we use them for. So I'm typically not going to ask you to turn in flowcharts and pseudocode along with your Java code, but I reserve the right at certain times to ask you to do something if it serves the purpose, okay? I would say another thing historically, in the beginning days, at least of my career, you know, back in the olden days, computer time was a premium. So, you know, at college, when I went to college, you had to like reserve an appointment, or your class had a specific hour that your class, you'd be waiting at the door like we do here, and the bell would ring and the door would open and all the people in the computer lab would get up and walk out, and your class would walk in and take a seat someplace at the computer lab, and for that hour you were allowed to write code, such as it was, and submit it to the computer, and your processing time would queue up, and maybe 5-10 minutes after you submitted your program, you'd get a report back that would tell you what errors it encountered. Maybe it didn't even compile, maybe it compiled but it ran, maybe it ran too long and it said, no, I'm not gonna let you do that. All kinds of stuff would happen. And then you'd have to try again, and you might run out of time. And then they had other open lab times like at 11 p.m. So you might be up there at the computer lab at 2 in the morning trying to get your homework done, waiting for a computer to become available. I mean, computer time was at a premium, and it was similar in business. My first job out of college, I was working for TWA in Kansas City, and we're just 4 college graduates that they stuck in the same team on the same project, and we each had our own assignment. But they put us in this little bullpen area. Each of us had a desk, we had an office chair, and we had this terminal sitting on our desk, you know, a screen and a keyboard, but we only had one cable between the 4 of us. So we would just trade off. Okay, it's my turn to have the cable, and so we could plug the cable into the back of our computer, and now we had the computer time and we could do our work. At the end of the hour, okay, it's my turn. Okay, let me finish up really quick. Okay, here you can have the cable. So only one of the 4 of us at a time could do any real work. The rest of us, we were sitting there with our paper and we were flowcharting and pseudocoding what we wanted to code in when it was our turn. In that kind of an environment, it makes a lot of sense to have you work on flowcharts, have you work on pseudocodes, maybe even write out on paper what code you're developing, even though you have no idea whether it will run or if it has syntax errors in it, okay? So at the time, it had a big purpose too. Now, computer time is so abundant. I mean, you have computers sitting here next to you that each one of them is more powerful than the entire computer that TWA was using to manage all the reservations globally. So that's not a problem anymore. There's not as much reason for you to sit and think about the solution. We think more in terms of agile software development lifecycle. So the idea is write some code and run it, see what it does. Oh, you don't like what it did? Change it, run it again, see what it does. And there's much more of a priority on quickly throwing something out there and seeing if it works than doing a lot of pre-planning. But I'll say the same thing I did before with the idea of using AI. If your brain can't code the solution, you're no good to anybody. So whether you write it on paper or you understand what the program's supposed to do in your head as you type it into Java code, either way, your head needs to know what you're going to do. So having a mind for design of algorithms is still very, very important, whether we do flowcharts and pseudocode ahead of time or whether we just jump in and start writing the code. So that's my main point here. So no, we're not going to do flowcharts and pseudocode, but I reserve the right to still pull it out of the toolbox because I know you guys know how to do it. Coding style is another aspect of software development, and I want you guys to think about this a little bit. You'll develop your own style, like it or not. What level of comments you add to your code, what naming convention you use for variables, how much white space, blank lines or blank spaces, tabs, things like that, how much of that you use. You know, in Python, column alignment was very important. If you indented a line, that meant it was within the outer line, right? There was a hierarchy that was imposed by indentation in Python. In Java, not so much. In Java, it's curly braces and semicolons. So as long as you follow the curly braces and semicolon structure, indentation isn't as important. So maybe some people will indent 2 characters, some people will indent 3, some people will indent 4, whatever. You'll develop your own style. As your teacher, I have developed my own style through 40 years of programming, and I will feel most comfortable when you turn your Java code in. It'll look best to my programming mind if you follow my style. So you may see times where I tell you, okay, there's 18 ways of doing it, but I want you to do it this way because that's what makes sense to me, and I'm going to be the one reading your code and giving you a grade. So please follow my programming style, okay? I probably want you to over-comment your code for sake of the class so that, and I say this a lot, that you know, if you write a crappy Java program, but you comment it very well, and I know what you were trying to do and what you were thinking, I can guide you as to, oh, I see what you were trying to do. Here's how you do that. But if you just write a bunch of gobbledygook and a semicolon, I don't know what you were trying to do there often, and I can't help you get to the goal you were trying to get to. So I'll probably encourage you to over-comment than I would expect you to do if I was paying you a salary to do it, right? But there are lots of standard styles out there. I gave you the link up here to one. And the Cornell one that they described, it's not original. I'm sure they got it from someplace, or somebody that worked in industry and then went to teach at Cornell came up with this document, whatever. But it's not bad. When I went out there and looked at that URL, when I was researching what the current state of the art was for how people describe what their programming style is, that one looked pretty good, pretty close to what I'm comfortable with. Except that lots of Java programmers, they'll type a statement and they'll put the curly brace on the same line at the end of the statement. I dropped the curly brace down and I put it on the next line in the first column again, so that when I look at my open and closed curly braces, they match up. That to me makes a lot more sense to my brain when I'm reading the code as to hunting for, okay, where at the end of which line is that hanging little open curly brace up above. So it just helps me. I know why it was developed that way. People did it that way back when we had these teeny tiny little screens and you couldn't fit very much on the screen at one time. And developers do better when they can see more of their code at a time. Again, just one of those brain things. And so by not wasting a line of code, it helped. But now we've got these huge, big screen, high resolution monitors, and you all are young enough, your eyes are probably still good, so you probably decrease the font down to where each letter is 3 pixels high and you can still read it. No, I need it big now. Even with the reading glasses, it's like, what? But that way we've got other ways of coping with how much text we want to see on the screen now. We don't have to conserve lines by putting a curly brace on the end of the previous line. So that's one of mine. There's some other minor stuff with how you name variables, and because again, historically, we didn't have all these fancy compilers and stuff where you can just put your mouse over some word on the screen and you get this big pop-up that tells you anything that you'd want to know about it. Back in the old days, you just had the text. And so we did a lot of stuff with how we named things would indicate things about what we were naming. So a function name, we would start with a capital letter. A variable name, we would start with a lowercase letter or some other notation like that. So when you see these naming guidelines and coding style guidelines, that's where a lot of that stuff comes from, is the idea that when you're reading your code, you can infer what it is, some meaning about it, by how it's named. Okay, so all of that aside, just to say, I would like for you guys to think about coding style and research some of the differences in it, and I think that's one of your discussion assignments coming up is, what did you find in differences in the way people specify? Because I'll tell you, when you get to working someplace, unless it's drastically changed, your boss will tell you, here's the document that specifies our coding guidelines, and you will make your code look like everybody else that works here, because it's a productivity thing. You want a programmer to be able to go work on any file in the repository and not be tripping over, why are there 10 comments to one line of code in this file, or why are these variables named radically different than the ones over here? You want some consistency to make it where any programmer can work on any part of the code, or at least that's the dream. Okay. Any questions? Okay. Next, what are we going to turn in? So you saw that folder that IntelliJ created, and it's got all these files and stuff in it, and we talked about the other associated files that GitHub may throw at you when you create a repository. I don't need to wade through all of that stuff usually in order to grade your assignment and see if you got the point of it, and all I really need is the Java file. So that's typically, again, unless the assignment says otherwise, I will commonly just want you to turn in the .java file. And that makes it easy. And if I need something else, I can ask you. At a certain point, I may just want you to turn in the URL of your repository. Now that has another caveat. If I have you turn in the URL of your code repository in GitHub, I kind of need access to the repository. And you got two ways of giving me access to your repository in GitHub. One is make the repository public. That means anybody out there can see it. You may not want to do that, right? You may only want to give people access to your repository if you're getting ready to go to an interview there, or something like that. The other way is to look at the list of people that you've given access to and invite them to see your repository as a collaborator. They can collaborate with you on this project. That's what I would recommend you do. You create a repository, you upload your work to it, and then you invite me, my school email address, to collaborate with you on that repository. And so that's now something you have to remember to do. So at some point, you may turn in your URL for your repository, and I may have to reach out to you and say, sorry, but I don't have access. Oh, dang it. So you go give me access and let me know, okay, now I can see it, now I can go in there and grade it. Probably doesn't mean a whole lot right now, but just one of these days when you actually see the email from me, you'll remember, oh yeah, he told us that in class. I need to give him access to my repository. If that's the way we're turning that one in. Make sense? So commonly you'll either give me the Java file and upload that to Canvas, or you'll give me the URL of your GitHub repository so I can go check that out. Okay. Yeah, and I've done a little bit of that, and I've probably talked longer than I wanted to. So I've already kind of walked through the IntelliJ thing once or twice, but that's kind of the next thing for you guys to do. One of the things that I do want to mention before I forget is, you saw when I looked to see if Git was installed on the computer, right? I just typed Git and hit enter, and oh, something happens now because I installed it. But before it just said, I don't know what you're talking about. I don't know anything called Git. But I used the where command. Let me make that bigger. Where, start in C: drive, and look for git.exe. So that's the command that I did earlier to see if where Git was installed on the computer. When I typed Git and nothing happened, I knew that Git was not found in any folder that was in the path on the computer, right? I can also just say path, and it'll tell me, here's the list of all the folders on this computer that I will go look in if you tell me something like Git. I'll go look in all those folders for it in my path, right? But if I want to use the where command, I can say, go look for this thing and tell me all the places in the C: folder and subfolders that lives. So what if I wanted to know where Java was installed on this machine? I could do that, right? But that's not the compiler, right? That's the Java runtime environment. But I could say, where is javac.exe, and that would tell me all the places on this computer that the compiler is located. So when I stop talking in a moment, one of the first things I would like for you to do is open a command prompt and do these commands. Look for java.exe and look for javac.exe. Because what I want you to do, just like with git.exe, I want you to be aware of where and how many times Java is installed and the Java compiler is installed on this computer. And you have that in the back of your mind at home too. Because one of the things that we ran into last week, I know this happens commonly, is if you build a a Java project, Java program, and you get it running in IntelliJ, and then you go to a command prompt and you say, okay, I want to run that command line program, and you just type Java in the name of the class, one of the things you're going to frequently run into is, oh, sorry, I can't do that. This Java class was compiled with a different version of the compiler than the runtime environment that I would be going to run it in. They have to match versions. And it might make sense. That should be intuitive, right? The version of Java that I compiled with has to match the version of Java I'm going to run with, or you could potentially run into problems, mismatches, all kinds of nefarious little things. So start becoming familiar with checking for that, because you will run into it eventually. Now, I will say this, if you're at home and you install IntelliJ, you could never open a command prompt, you know, as long as you have a career as a Java programmer, and just live inside IntelliJ. Because one of the things that the people that built IntelliJ did is they said, okay, we're going to make darn sure that we're compiling and running with the same version of Java. We're going to always point at the same one. So when you install IntelliJ, they install their own version of Java, the compiler and the runtime, and the two match. So with IntelliJ, you get one version of both of those things, and they always use that to make sure that their IDE never has that problem. Eclipse, the same thing, right? They try to control the environment. But the people that set up these machines may have just said, no, just install Java. So it's available, so we could use Notepad to do it. Anyway, you get the point. I'm hammering that to death, but be aware of and familiar with where Java, the compiler, and Java, the runtime environment, live on your machine, so that you're cognizant when you're trying to do stuff, you're trying to compile your program, you're trying to run your program, that the versions match up so you won't run into those kind of problems. Okay? Any questions? No? Wow. So have I talked you to death? Or did I just do a really good job teaching this week?
Second one.